So first of all, a couple of things. There's no lab this week. I will be in the lab room during your lab periods, so please feel free to come if you have questions or you want to go over anything, lab related, class related, or whatever. I'll be in there. The second thing is, even though there is school on Wednesday, we don't have class on Wednesday. Okay? So something to be thankful for. And then the third and last thing is Wednesday is the last day for withdrawal. Wednesday. And that's school-wide, so any of your classes, if you're thinking about possibly withdrawing from a class, Wednesday is the day you need to do it by, and you should, I would definitely recommend making an appointment with an advisor before you do something like that, because there's sort of complicated financial aid implications, or there can be, So anyways, that doesn't affect most people in here, but I know you should be aware of it. Any questions about that stuff? Okay, any homework questions you'd like me to go over? Okay. Well, we're going to get into a new topic today. It's kind of the start of the last topic. This is rotational kinematics. And it's very closely related to circular motion. You'll see a lot of the same stuff as circular motion. So related to circular motion. But here's really the difference. While circular motion is the motion of a particle along a circular path, rotational motion is the change in orientation of a rigid body. So this is a new thing, rotating about a point. Okay, so circular motion is you have a particle that's moving in a circular path. Rotational motion is you have some object that has length dimensions and does have an orientation. Remember that was the thing with a particle. We treat it like it doesn't have any length dimensions and we don't know anything about the orientation. Now we're talking about bodies that are, rotating like this. The way they're connected, so they're related because when a rigid body rotates about a point, every point on that rigid body is in circular motion around that about point. So I'm going to call this the about point. That'll keep coming up. But the about point for us is just the point that's fixed on this body. Like if you imagine this being like a hinge that this board can rotate around, that's the about point. So what I'm saying here is, so say that you have, you can see that these two things are different, right? That particle moving in a circle is obviously different from this board rotating around a hinge. But any point you look at on the board is traveling in a circular path around that hinge. Okay, those are supposed to look like circles, but okay. When we talk about rotations of rigid bodies, so let me get this down. So a rigid body. So unlike a particle, rigid bodies have length dimensions. And you can talk about their orientation. So, and orientations. You know, you can, orientations. You could paint a dot on one part of the rigid body and track where that dot is facing at any instant. You can't do that on a particle. There's no such thing as that. To talk about rigid body rotations, we need two definitions. Angular velocity and second, angular acceleration. Okay, so I'm going to start by defining those two things and giving some relationships that you can always use between angular quantities and the quantities like velocity and tangential and centripetal acceleration that we're used to. So I'll start with angular velocity. Angular velocity is how quickly and in what direction an object is rotating. This is always given, okay, so first we're always going to denote it with the Greek letter omega. That's a lowercase omega. It looks like a sort of a circular W. And the units for omega are always measurements of an angle over units of time. So in SI units, this is radians per second. One thing I want you to remember about this is even though we're dealing with radians for this, you can just leave your calculator in degrees because we're not going to use any sines or cosines with these radians. Okay. So you can leave your calculators in degrees. When I talked about velocity, regular velocity, before, I said that it's made up of two things. Its magnitude is the speed, and its sign, or its direction, is the direction the object is moving at that instant. Okay? And it's going to be similar with this. So angular velocity is its magnitude is the angle of rotation divided by the elapsed time. And its direction is given by the sign. Positive means a counterclockwise rotation. If you could choose this for yourself, you'd probably choose positive to be clockwise, but notice this is, we didn't get to choose. Positive is counterclockwise. And negative is clockwise. So let's see how this works. So let's say that a propeller is rotating clockwise at 2,000 RPM. And RPM stands for rotations per minute. And the question is, what's the angular velocity of the propeller in radians per second? Well, you can think of this as just a unit conversion. One rotation is how many radians?
2.
Right. I'm sorry, almost right. 2 pi. 2 pi radians. And 1 minute is 60 seconds. Okay. So the angular speed, just the pure angular change in the angle divided by the elapsed time is 2,000 rotations per minute. One rotation is 2 pi radians. 1 minute is 60 seconds. And you end up with a value of plus or minus 209.44 radians per second. Now you have to think about the sign. I said this is rotating clockwise, so is this positive or negative? Negative, right? So the answer is negative 209.44 radians per second. That's the angular velocity. Okay. If the speed of a point on the body is capital V, the speed of a point is equal to omega times r, where r is the distance from the about point. You can think of that as like the hinge to the desired point on the body. And okay, one thing that we have to be, I'm sorry about this. Let me change one thing. I think this will be clear. So let's say V is equal to, this is capital omega, okay? And let's say that capital omega is the angular speed and it's equal to the absolute value of the angular velocity. So all I'm doing, I could have put the absolute value in here, but basically what I'm saying is just take the positive value of whatever the angular velocity is, multiply it by the distance from the about point to the point you care about, and that'll give you the speed. So let me do a problem where we use this. So let's say that this board has a length of 1 meter. And let's say that the about point is 1/4 of a meter from the end. And let's say that this is the point P we care about. If the angular velocity of this board is negative 10 radians per second, what's the velocity vector of that point P? Well, first let's think about just physically, let's think about what that point P is doing. This is moving clockwise, so it's moving in a circle like that, this way. So what direction is that velocity vector going to be? Can you picture that? It's going to be, if this is the path of that point, the velocity vector is going to be tangent to the path in the direction of motion, so it'll be like this. But what we don't know yet is the speed. Okay, this part we kind of figured out based on what we knew about circular motion before and just knowing what the sign means for the angular velocity. But now we have to figure out what the magnitude of that velocity is. Well, the speed is, forget about the negative, and it's just equal to 10 radians per second times the distance from the about point to the point we care about. What's that distance from the about point to P? Yeah, 0.75. So the speed is 7.5 meters per second. And since that's down, the velocity of that point P is 0, negative 7.5. Let's think about another case where this time the about point is at the center. And let's think of a point A there and a point B there. Okay? And let's say the angular velocity is positive 5 radians per second. I have to give some dimensions. Let's say this is 2 meters. This is half a meter. The about point is right in the middle. What are the velocity vectors of the points A and B? Well, you don't have to do this, but let's start by visualizing the motion. This is positive, so is this board rotating clockwise or counterclockwise? Counter, so this point A is moving this way. And the point B is moving in this circular path. So the velocity vector of the point A is tangent to the path in the direction of motion. So that's the velocity vector of A, that's the direction. The velocity vector of the point B at this instant is tangent to the path in the direction of motion. So there's VB. So now we know the directions, we just need the speeds. So the speed of A is equal to 5 times what's the distance from the about point to A? 0.5. So we have a speed of 2.5 meters per second. Combine that with what we know about the direction and the velocity vector of A, since that's in the negative x direction, is negative 2.50. Okay? And then for B, the angular velocity is still the same. A single body only has one angular velocity, but the velocities of the different points are different. Okay? So the speed of B is still 5 radians per second times, what's the distance from the about point to B? 1. Yep. And so this is 5 meters per second. You can see that the velocity of that point is in the positive x direction. So the velocity vector of B is positive 5, 0. Any questions about that? Okay. So now we have to talk about angular acceleration. The angular acceleration symbol we're going to use is lowercase alpha, Greek letter alpha. Looks like a goldfish going to the left. And it is the rate that the angular velocity is changing. The units for angular acceleration are always an angle divided by units of time squared. And so the SI units are radians per second squared. You're not going to ever have to calculate the angular acceleration magnitude, but the direction of the acceleration magnitude is the same as it was for angular velocity. Positive is a counterclockwise angular acceleration. Negative is a clockwise angular acceleration. And here's something that looks familiar. If the angular velocity and angular acceleration have the same sign, what do you think I'm going to say? It's speeding up. So the object's rotations are speeding up. And if the angular velocity and angular acceleration have opposite signs, the object's rotations are slowing down. How did I write this before? So now if there's, like there was a relationship between the magnitude of the velocity vector and the angular acceleration of the body, there's going to be something similar for the tangential acceleration of a point on the body and its angular acceleration. So if the magnitude of the tangential acceleration of a point on the body is a tan without the vector symbol, then the tangential acceleration magnitude is equal to alpha times r, where capital alpha is the absolute value of little alpha, and r means the same thing it did before. R is the distance from the about point to the desired point. Any questions about that one? Okay, let's do a calculation with those. So now let's say our rigid body is like a wheel, a circle, and it rotates around the center. And let's say we have 2 points. Let's have one be midpoint between the about point and the top. So I'll call this point A. And then let's have one be at the edge to the left, and we'll call that point B. If this body has an angular velocity that's equal to positive 10 radians per second, and an angular acceleration of negative 20 radians per second squared, what are the velocity vector and the acceleration vector of points A and B? I also have to give a radius of this circle. Let's say this is 0.2 meters. Okay, well, let's first think about the directions of the things that go into the velocity and acceleration. For the point A, it's in a circular motion like this around the about point. The angular velocity is positive, so is this point moving clockwise or counterclockwise around that circle? One of you is right and one of you is wrong. Positive means clockwise. And so the the direction tangent to that path in the direction of motion is like this, so the velocity vector is that way. Yes?
Positive equals clockwise?
No.
Yeah.
Positive equals counterclockwise.
Sounds like that.
You're right. Thank you. Oh man, I got so flustered I erased my whole circle. Positive is counterclockwise, thank you. So it's going this way. So the velocity vector of A is like that. For B, that angular velocity is still the same. It's still moving counterclockwise. So it's going around this circle counterclockwise. So the velocity is going to be like this. Okay. Now let's think about the acceleration. If these are both in circular motion, at the point A, remember in circular motion, the acceleration is the centripetal plus the tangential. From this point A, what's the direction of the centripetal acceleration? That always just means toward the center. Okay. The velocity, the angular velocity and angular acceleration have opposite signs. So we know that the tangential acceleration, we know it's slowing down. So we know the tangential acceleration is opposite of the velocity. So the tangential is this way. Let's do the same thing for B. So the centripetal acceleration is toward the center. The tangential acceleration, since it's slowing down, we know it's slowing down, is opposite of the velocity. And now that we have all those directions, now we just need the magnitudes of these things. Okay, so for the point A, the velocity, the speed is equal to the absolute value of the angular velocity times the distance from the center to the point A. What's the distance from the center to A? Yep. So the speed is 1 radian per second. The velocity vector of the point A is in the negative x direction. So this is negative 1, 0. And now let's think about the parts of the acceleration. How do we come up with the, well, let's do the one that we've just talked about first. So the magnitude of the tangential acceleration is the absolute value of the angular acceleration, so 20, times that same r that we use for the angular velocity, so 0.1. And so this is 2 radians per second squared. I drew that tangential acceleration. You can see it's in the positive x direction. So the tangential acceleration vector is 2, 0. What about the centripetal acceleration? Well, we can calculate that the same way we did before. That's just v squared over r. And we already calculated that v was 1. So v squared over r is 1 squared over 0.1. And so that's 10 radians per second squared. We figured out that that's in the negative y direction. So the centripetal acceleration vector is 0, negative 10. Now it's just a matter of adding those two together. The total acceleration is the tangential plus the centripetal. So that's 2, 0, plus 0, negative 10. So 2, negative 10 meters per second squared. Any questions about that one for the point A? So now we'll go to the point B and do the same thing. Actually, why don't you take a few minutes and see if you can work through this, and then I'll go through it after you're done. Okay, so first, to find the velocity, the speed is equal to 10 times, what's the r value for the point B? 0.2. So this is 2 meters per second. We figured out before that the velocity vector is in the negative y direction. So the velocity vector is 0, negative 2. And then for the acceleration, the magnitude of the tangential acceleration is the absolute value of the angular acceleration, that's 20, times r of 0.2, and so you get 4 meters per second squared. We figured out that that's in the positive y direction. So the tangential acceleration vector is 0, 4. Then the centripetal acceleration is v squared over r. So that's 2 squared over 0.2. And so that is 2, right? 4 over 20. 20 meters per second squared. And we figured out that that was pointing in the positive x direction. So the centripetal acceleration is 20 meters per second squared. And so the total acceleration of that point B is 20 for x, 4 for y, meters per second squared. Yes?
Is the unit in meters or radian?
So for the angular quantities, the angular velocity and angular acceleration, it's in radians per seconds and radians per second squared. Once you do this calculation, you're back to the stuff that we're used to, and those are meters per second and meters per second squared. And the way it works, if you think of the multiplication, it sort of looks like it should be radians times meters per seconds, for example, for velocity. But if you remember, I don't know how many of you have in math talked a lot about radians, but radians is kind of like a unit and kind of like it's not, you know? That's why it's what you have to use if you're doing any kind of, if you're using trig functions or calculus with angles, you have to use radians. And so you can always think of radians as kind of not really there. It's really just, it's not there. It's just a reminder to you that we're talking about an angle. Any other questions? Okay. So pretty soon we're going to start doing kinetics with this stuff, and it's going to involve torques. But I just want to give you sort of a roadmap of all these things that, so we have all these particle quantities, translational quantities, let's call them, and we have these, we're building up these new angular quantities, and there are really close relationships with all of them. So I want to point out, just make a little table of all the things that are kind of similar between the angular quantities and the old translational quantities. So you can just think of this as similarities between translational and angular quantities. Okay, so over here, the translational ones that we've been using this whole time. Translational. And over here are the rotational or angular. So for particles, there's the velocity v. For angular, rotational, there's the angular velocity omega. For translational, there's the acceleration vector. For rotational, there's the angular acceleration. For translational, v and a in the same direction mean the object is speeding up. And v and a in opposite directions mean that the object is slowing down. For rotational quantities, omega and alpha in the same direction mean the object is speeding up. And omega and alpha in opposite directions means the object is slowing down. And now we get to the kinetic stuff. For translational quantities, resistance to acceleration was the mass. For rotational quantities, we're going to see that resistance to angular acceleration is a quantity called the moment of inertia, or the mass moment of inertia. I'll put that in parentheses. For translational quantities, the thing that causes accelerations is a force vector. For rotational quantities, I'm going to call it capital M, and people either call it a moment or a torque. Those mean the same thing. And there are also these relationships that we know that for translational quantities, V final is equal to V initial plus ATF. P final is equal to P initial plus V initial time final plus 1/2 A T final squared. And then 2 times A times the quantity P final minus P initial is equal to V final squared minus V initial squared. Well, these equations also hold with angular quantities in their place if you think about the position as the actual angle of the thing, the orientation. So these also hold omega F is equal to omega initial plus A time final. No, alpha time final. And then theta, that's the angle final, is equal to the starting angle plus omega initial times time final plus 1/2 alpha time final squared. And then 2 times alpha times the quantity theta final minus theta initial is equal to omega final squared minus omega initial squared. And then the last equation that we're going to get to is the thing that, for translational, the thing that causes accelerations is equal to an object's resistance to acceleration times the acceleration vector. For angular quantities, the thing that causes angular acceleration is equal to the object's resistance to rotation times the angular acceleration. So this is kind of like the big final result that we're going to get to. So just notice how similar all this stuff is, and that you basically, like if you're trying to remember this stuff, I mean, and I will give you all these equations on tests and stuff, but if you're trying to find sort of brain space for it, you really don't need any new brain space. You just kind of replace all the rotational things with the translational things with the rotational things, and all these equations still work. Okay? Okay, that's all. So yeah, feel free to come to your lab period on Monday or Tuesday. We won't have anything on Wednesday. But other than that, have a good Thanksgiving.
Did you scroll down to it?
Yeah.